Traditional video editing relies on the manipulation of isolated, two-dimensional temporal strips of media. For decades, the process has required an editor to sit in front of a timeline, manually aligning thousands of disparate moments by eye. This flowchart illustrates the inherent sequential bottleneck of that standard process. Syncing audio, cutting frames, reframing shots, and grading color must occur linearly. If a sync drifts or a camera angle requires adjustment, the entire workflow stops until human hands provide manual intervention. Treating physical reality, sensor data, and written narrative as a unified, queryable state machine allows us to bypass this manual assembly sequence entirely. The objective is replacing the rigid editing timeline with an autonomous, mathematically driven spatial media engine. To see this architecture in practice, we track a continuous physical event, a vehicle performing a high-speed maneuver through a complex environment. This diagram shows the three distinct raw data streams captured simultaneously during that event. We have ungen-locked spatial video from multiple lenses, physical telemetry containing GPS and motor bus data, and structured narrative beats. All three flow directly into a central ingestion bus. Integrating these inputs programmatically at capture transforms the data itself into a cinematic decision maker. When the vehicle whips into a wet gravel corner, it generates intense physical forces and rapid sensor spikes. The raw GPS data recording this maneuver updates between 1 and 5 times per second. Under heavy tree canopies, satellite occlusions and multipath signal bounces cause these coordinates to drift, creating elevation jumps and erratic positional mapping. To construct a usable environment, the ingestion daemon feeds this chaotic data into an extended Kalman filter. This split-screen graph compares the raw inputs against the mathematical output. On the left, scattered GPS points float erratically. By fusing these points with IMU acceleration curves, the filter dead reckons a smooth spatial trajectory on the right, eliminating vertex wobble. At the exact same moment, transient acoustic cross-correlation kicks in. Action cameras and field recorders rely on ungen-locked internal clocks, creating microdrifts in the audio tracks. The system analyzes the raw waveforms for high-frequency transients. A physical sync clap, a motor spin-up, or tires impacting the gravel provides the mathematical reference to phase lock every track down to subframe accuracy in milliseconds. Simultaneously, the geofenced script parser ingests the written narrative. The script is formatted as a structured JSON state machine, permanently mapping scene milestones to specific geographic coordinates. As the vehicle crosses an exact elevation threshold or geographic bounding box during the turn, the system flags the corresponding narrative story beat. The math stabilizes the path, the transients align the audio, and the coordinates trigger the script. A frame-accurate spatial foundation is built without a human editor opening a single media bin. With the exact physical trajectory secured, the stabilized data routes out of the ingestion daemon and directly into the Blender 3D environment. Inside this 3D environment, the physical camera rig that actually captured the real-world footage is discarded. The framing is entirely decoupled from the hardware. This diagram demonstrates how the stitched 360-degree video plate is projected onto interior proxy spheres. It acts as a live, high-dynamic range world environment shader. As the physical vehicle travels from sunlit clearings into heavy pine canopies, any 3D geometry placed inside the sphere automatically inherits identical ambient light, shadow direction, and chromatic bounce. Geometry nodes convert the GPX coordinate stream into a physical asset, a glowing, aerodynamic ribbon that follows the precise local Cartesian path of the vehicle along the ground geometry. Because the environment generates full Z depth mapping, this telemetry ribbon casts actual shadows on the asphalt and natively ducks behind three-dimensional trees rather than floating over the lens like a flat graphic. This enables a cinematic technique using 6 degrees of freedom. A virtual camera can fly freely through the reconstructed environment. A kinematic follow rig calculates the vehicle's velocity vectors, dynamically diving from a high-angle crane view down to the tires, seamlessly reframing around physical obstacles. The engine outputs multi-layer OpenEXR sequences. These massive files embed C-depth, surface normals, and cryptomatte isolation passes directly into the frames. Blender serves as a spatial bridge, severing the camera from physical reality to execute algorithmic cinematography. As Blender completes its passes, the multi-layer EXR sequences deposit directly into the local operating system's file directory. Running continuously in the background is the VFX Auto Ingest daemon, a Python script sitting precisely at the OS level. This image displays the underlying code structure. The script utilizes a watchdog observer that silently monitors the target render directory, waiting for incoming sequence frames. Large sequential files require brief transmission times. The daemon tracks these incoming packets until the file write locks settle securely on the drive. Once a debouncing period confirms the transfer is complete, the script triggers its next phase and reaches out to the active DaVinci Resolve instance. The daemon configures the system paths and loads dynamic libraries, establishing a direct connection to the Resolve scripting API. It immediately generates Open Timeline I/O data, reading the incoming media to automatically construct the exact timeline track hierarchy required for the project. The Python script then executes the Build Fusion Comp logic block, an instruction set designed to construct the multi-layer extraction pipeline. Watch the node graph construct itself. The daemon programmatically instantiates loaders, vector blurs, and merges, dropping them into the workspace at specific grid coordinates and drawing the connections. These nodes are instantly wired to extract the exact Y-depth and matte passes previously embedded in the Blender EXR sequences. By bridging the headless 3D rendering pipeline directly to the final compositing environment, this script handles the entire extraction process with 0 human clicks. Inside Resolve, the system evaluates spatial proximity logs between the drone and the vehicle. If the drone is directly overhead, algorithmic switching logic automatically cuts to the wide aerial camera. In Fusion, channel booleans read the 16-bit float EXR Z buffer, mapping the depth data directly into atmospheric haze and depth of field falloff. This telemetry graph shows the physical IMU yaw and pitch extracted during ingestion. The script writes keyframe curves directly into CardaVR node parameters. As the telemetry spikes, the virtual camera automatically banks into the turn. The Fairlight audio engine responds to the same performance, binding EQ filters directly to vehicle speed and wattage channels, dynamically ramping up wind filters during descents. When the narrative state machine fires an SSML dialog trigger, sidechain compressors listen for the exact cue, precisely ducking the ambient wind stems to make room for the synthesized voice track. Subjective, manual editing decisions and sound mixing curves are replaced entirely by reactive mathematical functions. Ground truth physical telemetry directly drives the final cinematic output. This unified 3-panel grid branches out from a single trigger point. A drop folder ingestion generates 3 distinct master outputs in parallel, completely removing manual timeline assembly from the equation. The first output is a cinematic 4K flat master. It features dynamic virtual camera moves, drone cutaways, and a properly ducked narration track sitting over the world-anchored telemetry ribbons. The second format is an interactive 6DOF VR master. It places the viewer inside the full 360-degree sphere, complete with spatial ambisonic audio and real-time 3D gauges embedded into the scene geometry. The final deliverable is a spatial telemetry archive, syncing the finalized video timeline to a live MapLibre terrain dashboard, displaying the elevation profile and electrical logs. Whether it is tracking a high-speed vehicle or plunging down a steep ridge in a continuous dive, the physical reality dictates the visual framing. In this architecture, the user is no longer a manual assembler of temporal cuts. The user designs the narrative state machine, engineers the pipeline, and lets the math edit the spatial reality.